Hi, my name is Jason Frazier. I'm an engineering lead here at Ekata, and today I'm going to be talking about scaling our identity graph with Redis on Flash. So here's a quick agenda just before we get started. I'm going to start off by kind of giving a brief overview of what Ekata is, who we are, what we do in general. Give a little bit of a background history about our identity graph. I'm also going to talk about some benchmarking we did before we ended up on Redis on Flash. Then also just talk about Redis on Flash in general a little bit, kind of what made it attractive to us and why we decided to go with this solution. And at the very end, I'm going to be talking about some kind of key learnings and basically things that we've learned along the way since actually implementing the solution roughly about 2 years ago at this point. So to start off, basically, who are we? So here at Ekata, we focus on delivering best-in-class identity verification solutions. We do this via 3 main products. The first product is our transaction risk API. This API was basically built specifically for with models in mind and has an emphasis on low latency. Our identity check API, which is specifically built for decision platforms, and our Pro Insight platform or product, which is basically built for manual reviews. All these products are basically powered by the Ekata Identity Engine. The Ekata Identity Engine basically has 2 main data stores behind it. Our identity network, this is basically our internal behavioral graph. This is where we store a whole bunch of things like how often have we seen this address with this person's name, or how often or how many times have we seen this phone number come through in a transaction in the last week or so, and the various velocities between all those different points. Specifically in this talk, I'm going to be talking about our identity graph, which is basically where we store a whole bunch of different information from various providers. And this is where we store all of our people, phone numbers, addresses, and all their various links in between them. So a little bit more history about us. So we are a global company. We have 4 main offices. We have an office in Seattle, Amsterdam, Budapest, and a newly opened office in Singapore. We have a bunch of different customers all across the globe with over 25,000 Pro Insight seats. And we see over 2 billion queries annually. Basically, who do we work with? We're with various different companies, such as retailers, marketplace companies, fraud platforms, travel and hospitality, as well as major credit brands. So let's kind of dive into it. So I'm going to I'll talk about our identity graph in general. So I'm sure a lot of people watching this are familiar with the show Friends. So this is sort of a representation of what our identity graph looks like with the show Friends in mind. So here we have a whole bunch of different entities. In our actual identity graph, we have over 5 billion entities with over 8 billion links between all of them. And with all these different entities, you can see we have Rachel Green. Rachel Green used to live with Monica Geller. So they have a link between this address. And Rachel Green also has a link to her telephone and her email and a past address. Monica is married to Chandler, so they have a person relationship. And Chandler used to live with Joey, so they also have a linked address together for their previous address they used to live in. So some key requirements on this graph is basically latency is one of the most important factors in here. So we expect our subgraph retrieval to be less than 20 milliseconds of P99 latency. To achieve that with some of our calls, because some of our calls are 3 to 4 depth calls, and we still expect those 3 to 4 depth calls to return in under 20 milliseconds. For this to actually be attainable, we actually expect our data store latency to be less than half a millisecond. Because if you start adding in things like network latency, that half a millisecond retrieval of the database plus the network time will basically turn that entire request into over a 3, 4, maybe 5 millisecond call. And we have a very, very sensitive, our application is very sensitive to latency just in general. One singular request, just due to the subgraph retrieval, can turn into hundreds or thousands of sub-requests to fill the overall request. Like if I search for a person, once I get that, it'll fan out and start searching for all the addresses. Then for all of those addresses that got fanned out, it fans out all of those addresses at the same time. So it very quickly can turn into hundreds or thousands of queries. Our throughput requirement is we needed a database that could, or a technology that could support over 350,000 requests per second. And what's very standard nowadays is make sure that this is stable and highly available. We use Redis on Flash as a primary database, and so we can't have any downtime whatsoever. So we had a key requirement of at least 4 nines of uptime, and it must be highly available across multiple AZs, and there must be replication within the database. So if a failover were to happen in the cluster, it should be able to automatically recover that without any kind of data loss. So here's kind of like a little bit of brief history kind of about the technology. So when we first started out, we just used Postgres once we started up. This actually worked fairly well, because at the time our dataset size was fairly limited. We weren't getting very much query volume. We didn't have that big of an emphasis on latency, so I mean, this did the job and it did well. But as we started expanding, basically the requirements started to change, just like any product. And after that, we moved over to Titan Cassandra once our dataset size started to grow a lot. This worked fairly well for us. This scaled well. It did what we needed to do. But there was basically a lot of latency problems and stability problems. Actually managing the cluster, basically there's a whole bunch of problems with actual cluster management. And then there was a lot of latency issues, like our P99s were well in the hundreds of milliseconds. And then there was just a lot of features on this technology that we just didn't use. There was just a lot of just wasted use on this technology. Because of that, we really started to analyze in our use case and started to optimize. And so from here, we actually started using ElasticCache and Redis as our primary data store. This worked because at this point, we actually flattened our database. Because we don't allow any kind of free-form queries, we know exactly what queries we're going to be calling, or basically what queries we're going to be searching our graph on, so we can start optimizing this. So we flattened our entire data structure into just key value pairs. We stuffed this all into ElasticCache. Traditionally, we only had US and Canada data. So basically, when we got new data, every time some provider gave us some new information, there's a good chance we already had that information, because I mean, the US and Canada is only so big. There's only so much new information that can happen within a couple of months. So our dataset size stayed relatively constant, grew very slowly over time. We started running into a problem as we started expanding out globally. Once we started getting global data, we were now pulling in entirely new countries. So once we started, like for example, let's say we pulled in like Germany, for example, if we didn't have anything on Germany at the time, basically all of that was a complete or a whole country addition to our dataset size. So our growth really started to explode. And at the time in ElasticCache, this has since been changed, but at the time when we made this switch, there was a limit of 15 shards in ElasticCache. 15 shards or 30 with a replication factor of 1 meant we can only have up to 15 nodes in our cluster, and nodes only get so big. And basically because of that, there actually was more or less a hard limit as to how big of a cluster we really could have made. And once we started expanding globally, we realized that we very quickly were about to reach that limit. And so that's kind of what sparked this entire journey of kind of reevaluating database technologies and how we actually ended up on Redis Labs and Redis on Flash. Once our dataset size started exploding in size, we realized that we need to find a new technology to be able to actually handle this. So as I mentioned, we actually basically this is kind of what our identity graph looks like when stored. We basically flattened our entire structure. So it's basically stored as key values. The key being a UUID of that specific entity, and the value being the various attributes. Like for example, a person might have ID 1, and then the value will be the attributes of that person, like their name, birth date, or or various things like that, as well as it also has the links that it's linked to, which are UUIDs to various other entities. On top of that, we also have our own, what we've called the shape language, which is basically what we use to query our database. On the right side of the graph, or right side of the screen, we can see an example query. So basically here, I'm asking for an address. So I'm basically searching our graph for an address. And I'm saying for that address, I want so these two numbers. The first number is current, so people currently there, and the second number is historical, so people who used to be there. So give me 5 current and 5 historical people for this specific address. And then for all of the people that get sent back on that request, I also want 5 current and 10 historical phone numbers for all of those people, 5 current and 10 historical addresses for all those people. And then for all of those addresses, I also want all of the non-addresses that are linked to that address. So here you can see this is a for-depth call, and here you can really see why we're so sensitive to latency. So that address is asking for at least 10 people, and for each of those 10 people, we're asking for 15 phones, 15 addresses, and 10 more people. And then for all of those 15 addresses, for all of those 10 people, I'm also asking for all the non-addresses. So this very quickly turns into a lot of queries, and that's what makes us so latency sensitive. So even in our database, if the P90 or what the P99 of the database is more like our P50, because one singular request is easily going to hit that P99 threshold immediately. So because of this, because of the problem of scalability, we started benchmarking various different database technologies. To do so, we used a benchmarking tool called Yahoo Cloud Serving Benchmark. We decided to use the same tool to basically get rid of as many variables as we possibly could. We want to make all of these benchmarks as fair as we possibly could. And we did this basically in 2 rounds. Round 1 was essentially what we did is we loaded a whole bunch of pseudo data into the database, and then just performed a whole bunch of GET requests onto that database to see like some initial latency benchmarks. And if the initial latency benchmarks looked good, we then went to a second round of testing, where essentially we actually loaded in a production size cluster with production data and actually started benchmarking to see what we would get in a production setting. So the first 2 database technologies that we looked at was Cassandra and MongoDB. Pretty much the reason we decided to look at these mainly was we knew for a fact that they could scale with they could definitely scale with the growth that we were seeing. There are many use cases and case studies on Cassandra and Mongo in clusters that are hundreds of nodes big or thousands of nodes big, holding up to like petabytes of data. So we knew for a fact that these technologies could easily handle the scale. These also had a very good community around them. I mean, they're fairly popular technologies. The overall community surrounding them is it's very mature, and they're very helpful. Unfortunately, there was both of these ended up failing our first round of testing due to latency. On the right side, you can see the actual benchmarks we did. Cassandra and Mongo both had a P99 latency of 18 milliseconds and 16 milliseconds respectively. So unfortunately, they didn't meet our latency needs. They also just weren't very well suited for our use case. Cassandra and Mongo have a whole bunch of features around them, and we strictly just need basically a key value store for lookups. We didn't really need anything else on top of that. So there's kind of just a whole bunch of things that were wasted here. And on top of that, there's just a whole bunch of learning curve. We had already had our database in Redis for multiple years at this point. And no one on the team actually knew a whole lot about Cassandra and Mongo. And so switching to a whole new database technology would require a whole bunch of learning across the team, or if anything, even just hiring a whole new person. So because of that, like I mentioned, both of these actually failed the first round. After that, we started looking at Couchbase. So at the very start, Couchbase actually had very promising latencies. Our initial pseudo data load testing showed some P99s of under 1 millisecond. So it actually did pass the very first round of testing. There's some very good support surrounding this. Basically, the company that owns this technology was based out of Bellevue, which is not too far out of Seattle, which is where our office was located. So they actually helped us out quite a bit for doing our benchmarking to make sure we were squeezing out as much performance as we possibly could with this. It was also a fairly good fit for our use case. While there was a whole bunch of features, just like Cassandra and Mongo, there was the ability to just kind of disable them or just not install them on the cluster. So we weren't really kind of just like wasting resources on all this stuff we weren't using. Couchbase also is strictly a key value lookup, which is exactly what we're looking for. So after the first round of testing, we ended up passing and actually loaded up a full production-sized cluster. And unfortunately, this is where the cons started showing up. So like most technologies, Couchbase requires all keys to be stored in RAM. But unfortunately, there was quite a bit of overhead per key. There was well over 100, 150 or so bytes of overhead per key. And that doesn't, that's not the biggest number, but that times 3, 4, 5 billion turns into a very, very large number. And basically the size of the cluster we needed was actually completely dictated by our keys. The size of our cluster was basically the minimum cluster size to actually just hold all of the keys in our database. And that cluster actually ended up being bigger than our Redis database that we were already using. And then because of that, there were some latency problems at scale because pretty much the only thing being stored in RAM was the keys. All the values were being stored on disk or flash, whatever's on the node at the time. And so because of that, we started seeing some latency problems at scale. I have once again, I have the benchmark on the right-hand side, and the P99 started to push toward the 2 millisecond range. And at that point, that was still way too much for us to keep going. So unfortunately, this ended up failing round 2. So after all this, we kind of took a step back and we thought, why don't we just stick with ElasticCache? We like it. We know it works. We like it. It just works. Some pros to this: get the same performance. Like I said, we know it works. It has the performance we want. We have the latency requirements that we need. It's familiar technology. We use Redis all over our applications for various caches and other data stores. And it's the same Redis protocol we've always been using. I mean, Redis is Redis. It's basically plug and play. As long as it has the same Redis protocol, we can basically just point our application at it and it just works. Really, the biggest con here was cost. As some of you are aware or may or may not know, there's quite a large upcharge on nodes for ElasticCache. So ElasticCache actually gets very pricey very, very quick. And so this is probably one of the biggest cons, that it just costs a lot of money. And like I mentioned earlier, at the time, there were some scaling issues. There was a 15 shard limit. And this actually recently been upped to 250 shards. But at the time of doing this testing, there was a hard cap. There was a way around this, but it was nothing that was very simple. I mean, we could have manually kind of like partitioned our data and used 2 separate ElasticCache clusters to hold 2 different pieces of our data, but then that starts getting complicated very quick. And we were trying to go for a nice, simple solution. So because ElasticCache was expensive and had this limit, we thought, why don't we just self-host our own Redis cluster? I mean, we can just spin up the nodes ourselves, spin up Redis and do that. The same pros as before. We have the same performance, familiar technology. Redis is Redis. And now cost is now a pro because we're no longer paying this upcharge on ElasticCache. We would actually cut, 20, 30 something % of the cost off of all this. And we also would remove the scaling limit. We could spin up our own Redis cluster as large as we want. We don't personally have any limit to how big we can spin up a cluster. But some of the cons of this is just kind of the management overhead. Managing your own cluster it's not the easiest task in the world. Being on ElasticCache, a fully managed solution, we kind of just spin up the cluster and kind of just forget about it. We know it's going to take care of itself. It's fully managed, so it's going to be taken care of for us. We don't really have to think much about it. And then there was kind of in the same train of thought, it's kind of some scaling issues. Self-hosting your own over 4 terabyte Redis clusters, not the easiest task in the world. And there's a whole host of problems that sort of pop up once you get into very, very large clusters. So after all this, we ended up finding Redis on Flash. So there's some key features that made Redis on Flash very attractive to us, mainly surrounding the fact that it supported flash storage. As I'm sure everyone here knows, Redis traditionally holds everything in memory, which is what makes it so blazingly fast. But Redis on Flash allows flash storage to be used on your cluster. And with this, NVMe volumes were really kind of like the big game changer here because they're very highly optimized and do provide RAM-like latencies even when we have to do a lookup from Flash. We also get better utilization of node resources. We're not basically just spinning up huge beefy nodes just because we need huge amounts of RAM. It's much lower cost, as I'm sure everyone knows. Flash storage is substantially cheaper than RAM. At the end of all this, we actually did the calculations, and the cost per gigabyte of our data and our data store actually decreased by 60% after migrating to Redis on Flash. And on top of that, the number of nodes needed in our cluster actually decreased by 40%. That's because, I mean, you can put a lot more, you can attach a lot more flash storage to a node than you can just RAM. So we weren't just using massive nodes just for the RAM. And on top of this, it wouldn't really require any change to our existing infrastructure because, I mean, Redis is Redis. So really, why did we choose it? Easy to integrate. Like I mentioned, Redis is Redis. We don't really need to do a whole lot to integrate. We more or less just need to spin up this new cluster, load it with data, and then just update the endpoints that our application was pointing to. And after that, it just kind of worked. And on top of that, we also got to keep the same fully managed solution that we were used to. Already. It required no extra training on our end. We didn't need to manage our own cluster or do any of that. And they also provide very helpful 24/7 support in case anything were to happen. And on top of this, in all of our testing and in production, we actually didn't see any change in our latency. We still see like a 0.1 millisecond latency or lookup latency even during our peak traffic times. So here's actually a screenshot from our actual Redis Labs dashboard. So you can see we were running at the time about 168, roughly 170,000 operations per second. And we were still running at about a 0.14 millisecond lookup time, which is great. So now after we migrated to Redis on Flash, which was at this point roughly about 2 years ago, there's some key learnings we've kind of learned along the way and kind of operational learnings that I'd like to talk about. So one is kind of just what really is one of the bigger differences between ElasticCache and Redis Labs. So one thing is in ElasticCache, so I guess Redis in general is a single-threaded process. Therefore, you're not really able to take advantage of multiple cores in your node. So we had these huge nodes in our cluster with a lot of CPUs, basically just using them purely for the amount of RAM that they were using, just to use one singular CPU on that entire core. I don't know if many people who have ElasticCache clusters out there have looked at their ElasticCache dashboard, but you'll notice that the actual CPU utilization of your node is probably less than 5%, is a pretty good guess. And on top of that, basically you had master nodes and replica node, or your slave nodes. And basically your replica, or all of your replications, all those nodes just sat idle just in case a failover was going to happen. So basically we had 15 master nodes and 15 replica nodes. All the master nodes were serving production traffic, and all the replica nodes were basically just sitting there idle, eating up money, just kind of sitting there for just in case something happened to fail over. Whereas in Redis Labs, it actually runs multiple Redis processes on every node. So you're actually able to utilize pretty much every CPU on the node. And every Redis process and every node has a mixture of master and slave shards on top of them. I have that denoted as master shards as white and slave shards as gray. So there's there's a mix of master and slave shards per node. And so you're actually utilizing a lot more of the node in general. And so one main thing that we noticed right away is kind of like hot pockets in our data. So once again, here's another screenshot of our of our Redis Labs dashboard. So there's one key metric called values in RAM. So basically, how many values do we have that actually exist in the RAM in the database at that time? And another metric of RAM hit ratio, basically the ratio of values looked up that come from Flash versus values that got looked up that came from RAM. So we have billions and billions of keys in our database, and only 330 million keys in RAM at any given time. And that's less than 10% of all of our values. And this actually provides us with over 90% RAM hit ratio. And so because of this, we actually more or less, it's almost the same as like ElasticCache. We're serving a very large portion of all of our requests from RAM, but all of the cold values that just never really get called, we get to store on Flash, which provides us substantially bigger cost savings. There's no real point to hold all of these values in RAM when they're just never getting called. And so this is actually something we didn't know about before this migration. It was something that kind of just came up as kind of a happy accident, I guess is the way to put it. But this is just something that it's good to know about, is to always know your data set, know all of its use cases, know how it's being used, and you can also optimize for it. One other thing that we spent a lot of time on is compression. Our overall database size is well over 10 terabytes in size, but we actually get over a 70% value compression using a custom Redis codec. We use Facebook's Z standard compression using a custom dictionary. And the reason we used a custom dictionary is because all of our values are very small. Like it's 70% compression is not a very substantial number. If you're thinking, oh, you have a huge file, like some huge text file, you gzip some huge big text file, you get a huge percentage of compression. But when you're talking about very small values, we get over 70% compression on very, very small values. And it pretty much directly is cost savings. We only need to store about less than 30% the actual database size. So because of that, we need 70% less size in our cluster, 70% less data to store. And so therefore, you just need an overall smaller cluster to actually hold all of that. And one thing that we're actually currently working on that's not supported at the moment is using binary keys. All of our keys right now in our cluster are just plain Java UUIDs. And so storing each key as a string is about 36 bytes for UUID. But if we were to store it as binary, it would actually be stored as 16 bytes. So that's a 20 byte saving per key times billions of keys. Turns into a very big number very quick. Unfortunately, this is not supported, and we're actually working with Redis Labs right now to get this resolved. But this is another thing we're looking to do for extra compression that we can get out of this. Now, lastly, I kind of want to talk about a few operational challenges that we've experienced. One very, very big one that everyone on our account knows very well, that we've worked with them multiple months on, is something that we've kind of dubbed dirty key eviction. So with Redis on Flash, you can either store your value in RAM or a value exists in RAM or it exists in Flash. So when you actually set a key in your database, when you first do that initial write, that value only exists in RAM at the time. And then eventually, once the RAM fills up, and then the cluster starts evicting values out of RAM and onto Flash, the cluster actually does a check. As it's evicting a value, it does a check. It says, does this value already exist in Flash? If that answer is no, the cluster says, okay, well, I need to write this to Flash before I can evict it. And so it'll actually perform a write within the cluster and write that value into Flash and then evict that value out. If the value did exist in Flash, the cluster will say, okay, does this value already exist in Flash? And it'll look and then say, yep, this value already exists in Flash, and then it'll just remove that value. It doesn't need to write anymore. And so because of this, if you have, and so our definition of a dirty key is basically a key whose value exists in RAM, but that value doesn't already exist in Flash at that point. At the very start, we didn't really know about this, and when we actually put a cluster into production, a whole bunch of values, as production traffic started getting up, and the RAM actually started holding the actual hot values of the cluster, not just the order that we happen to set them in. We actually started evicting tens of hundreds of millions of keys out of RAM at the same time into Flash, and that was causing tens of hundreds of millions of writes simultaneously into the cluster. And it almost basically grinded the entire cluster to a halt because so many of these write operations were going on, and it couldn't actually respond to any of the get operations at the time. On the right-hand side, you can see some metrics that actually pull from our Redis Labs dashboard once again. These are basically the two main metrics we look at before we put a cluster into production. You can see there's a box called total keys. So we can see in the total keys, there's about roughly 5 billion total keys in the cluster. And then there's this very important box called values in Flash. Basically, how many values exist in Flash. And so if there was to be a dirty key, that means that there's a value that doesn't exist in Flash. And so when we first load this cluster, we see that there's about 5 billion keys. But for values in Flash, we see there's maybe only, 4 billion keys in Flash. That means that there's roughly a billion dirty keys in our cluster, which means we could potentially see 1 billion writes onto the cluster as things start getting evicted into Flash. So the way we solve this actually is once we load our database, we actually go back and we basically touch every key in the database once. Doing this basically ensures that everything in RAM gets cycled into Flash before we start pushing this before we push this into production. And by knowing that we cycled everything out of RAM, we can guarantee that every dirty key has now been cleaned. And then one other thing that we had trouble with at the very start was how to properly handle node failovers. With Redis on Flash, basically when connecting to the database, we provide an initial endpoint for our client to connect to. When our client establishes a connection with the cluster, it calls basically the cluster nodes command on the cluster. And the cluster nodes command basically asks the cluster, hey, give me your topology, or give me all the nodes that exist in your cluster. And then the client will establish a connection with all of those nodes. However, we'll just say 10. So your client will establish a connection to all 10 nodes. And then let's say one of those nodes fails. If one of those nodes fails, basically the cluster will internally update its own topology to start pointing to the replica of that node, or all the replicas of that node that failed. But our application still had an established connection to the node that was down. So even though the cluster had internally failed over and already updated its topology, our application didn't know that and was still trying to send requests to the downed node at the time. So the way we got around this is basically how to handle timeouts within the cluster. So we basically added a timeout, or some timeout handling around the cluster, basically that says, hey, anytime I receive a timeout from one of my GET requests, basically ask the cluster for its updated topology. We can do this because historically we've had a extraordinarily stable cluster. We never see any timeouts or any kind of halts in our cluster at all. So basically we can make the assumption that if we're getting timeouts on our cluster, there's something up, something's wrong. We should refresh, reestablish our connections, update the topology of the cluster, and then go from there. So now what happens when a failover happens? So let's say we have 10 connections to 10 nodes. A node fails over. Our application starts timing out, and when that happens, it'll start calling cluster nodes against the cluster again. And then once the cluster internally updates its topology, it will finally return the newest topology to our application. And then from there, it'll establish 10 new connections to all the 10 brand new nodes. And then we're all working again. The last thing was the lack of API support. Once we actually moved to this, there actually was no API for Redis on Flash. We had a whole bunch of automation centered around the creation, destruction, and loading of all of our clusters. And once we moved to Redis on Flash, initially there was no API support. So all of our existing automation for all of this just didn't work. We had to manually get our cluster spun up, and then we had to, or once that was manually spun up, then we were able to run our automated loading. But if we wanted to tear down a cluster, we had to manually tear all of that down. Recently, there's been a lot of work going into API support. As of right now, there is not the ability for us to personally spin up and down our own clusters. There is the ability for us to spin up and down our own tables within existing clusters, but that last little bit of functionality of actual cluster spin up and down is still not there, which I believe should be coming sometime in the future. And so, yeah, that's more or less it. That's how we ended up on Redis on Flash and kind of our journey along the way. Let me know if you have any questions. My email is down below. Feel free to reach out to me, and I'm happy to answer any and all questions. Thank you.